For decades, network traffic modeling relied on the 1999 Dinitz-Garg Goemans, or DGG, cost conjecture. Refuting this conjecture requires a shift toward arithmetic geometry to reveal why discrete network rules eventually collide with the physics of continuous fields. The text on the left highlights the core assumption of the DGG conjecture, that single-path routing can always match the energetic cost of a split fractional flow. It treats the network as a purely discrete system. To see the flaw in the logic, we have to look past discrete nodes and edges. We must treat the network as the skeleton of a smooth algebraic variety. Reframing the problem as quantum geometry exposes the global topological boundaries that govern how traffic actually moves through a system. This flowchart illustrates the Adelic Langlands dictionary, mapping discrete graph rules directly into a continuous moduli stack. In the quantum code subspace, fractional flows map to a protected ground state, while unsplittable constraints manifest as anionic topological defects. Calculating the raw energy states of continuous vector bundles shifts the problem from counting discrete flow units to analyzing a structural geometric height. This provides a different mathematical basis for measuring network cost. We can observe this transition in Dmitry Rybin's 7-node network counterexample. This specific network is defined by 3 integers, a base flow scale of 10, a demand variation of 5, and a topological gap of 1. As shown, we map these variables onto a continuous number line as geometric ramification points, xb, xm, and xg. Point xb sets boundary conditions, xm dictates maximum fractional splitting, and xg generates the singular twist creating the physical obstruction. These 3 points define the topological boundaries of the quantum model. They are the structural origin of the failure in the DGG conjecture. We calculate the energetic cost using the Grothendieck-Riemann-Roch equation. The continuous integral on the left measures the energy of a smooth path across the unramified parts of the curve. When the network flow splits fractionally, it remains in a zero-syndrome quantum state, entirely within the protected code subspace. Evaluating this state yields an Arakhelov energy of exactly 58 units, our absolute geometric minimum cost. In a perfectly continuous system, the DGG conjecture would be valid because the flow can rest at this 58-unit energy minimum. The problem arises when we enforce a discrete, unsplittable path. This forces us to include the discrete summation term on the right side of the equation. The point xg introduces a singular twist. Forcing a discrete path here requires crossing a defect line marked L sub x. Substituting our Rybin variables produces a non-vanishing phase shift of e to the 2 pi I over 15. This phase shift ejects the state from the protected subspace. The resulting energy penalty of +2 units drives the total cost of the discrete path up to 60. This comparison proves the DGG conjecture is false for this system. The discrete path requires 60 units of energy, which is strictly more than the 58 units required for the fractional path. Take a moment to calculate the minimum budget multiplier needed to bridge this gap. Dividing the discrete cost of 60 by the fractional cost of 58 reveals a ratio of approximately 1.0345. This arithmetic gap confirms that discrete quantitation can decouple from continuous energy minimums, making the original 1999 assumption mathematically impossible. While the gap refutes the conjecture, we can stabilize the system by applying a universal budget relaxation multiplier of 1.12. Under this renormalization, our energy cap expands to 64.96. As shown in the right column, the 60-unit discrete state now falls below the ceiling, allowing the unsplittable path to exist within the energetic thicket. The expanded geometry provides the slack necessary to absorb the destructive phase shift. These gauge fluctuations act as a screening mechanism that stabilizes the localized defect. Expanding the permissible energy capacity transforms a destructive anomaly into a stable macrostate. Computer-assisted searches across infinite families of these distorted graphs confirm that even as boundary and obstruction parameters are pushed toward infinity, the cost ratio remains below this 1.12 threshold. Applying this specific multiplier across the entire Adelic Langlands landscape permanently closes the arithmetic cost gap. Forcing discrete rules onto a continuous universe reveals mathematical fractures. However, the Adelic geometric perspective provides the exact amount of slack required to stabilize network flows once and for all.